So getting data about the image is important. Some data that we need to know about the image that's useful is image.format. Okay, so these are, once again, these are getter methods for that image object. So image.format returns a string that tells us what kind of image it is. Image.size will return a tuple that has the width and the height of the image in pixels. And image.mode will tell us the mode of the image. Now, it could be RGB, it could be indexed, or it could be RGBA, which stands for red, green, blue, and alpha. That's an image that has the transparency channel associated with it. Okay, so if I open a ping file and it says RGB, that means that file does not have transparency information associated with it. If it says RGBA, it's got 4 channels. One of them is for transparency. So I use that information mostly, right? Mostly this information here, because if I want to reduce an image by half, or I want to cut an image to half the size, half the height and half the width, which is actually a quarter of the image size total, I need to know these numbers because I'm going to say, if I want to reduce it by 50% in height and width, I just take these numbers and divide them in half. And then I know what the new height and width should be. So that's how I use that information. So when I crop and resize an image, here's how it works. Now, cropping an image is when we take a subset of an image, a part of an image, and keep only that. We don't change the size of that part of the image. We just get rid of the other stuff. So for example, if that black square is my original image, I would say that that image is 1200 pixels wide by 700 tall. So the upper left corner of that image is pixel 0, 0. This pixel all the way down here at the bottom right-hand corner is 1200, 700. Those are important things to know because I want to know that information so that I can tell Pillow, using numbers, what part of the image I want to keep. And so the way I tell Pillow what part of the image I want to keep is by using image.crop. And you'll notice here, because I'm pointing it out to you, that there are 2 sets of parentheses. One set, the outer set of parentheses, is the parentheses that define the arguments for that method. That method takes one argument. That one argument that it takes is a tuple that has 4 numbers in it. That's why we have 2 sets of parentheses, one for the arguments and one for the tuple. If you forget, it's going to give you an error because if you forget one set of parentheses and you just put 1, what you're giving it is 4 arguments that are integers, and it doesn't understand that. Why does it want a tuple with 4 things? I don't know. That's just how the person that wrote it just decided that. If you write if you write additions to Python, guess what? You get to decide that. You can decide whatever you want. And let me just tell you, people decide some really weird crap. So the tuple, what does it represent? 4 numbers. This is the X and Y coordinates for the upper left part of the crop. This is the X and Y coordinates for the lower right corner of the crop. So it's just like when you're like doing this to frame your shot, like if you're directing a movie, right? You've all seen people do that. You know what it means when I do this. I'm defining a square, aren't I? That's all we're doing here with the red dots. So I'm saying the coordinates in this image of that red dot and this red dot are going to give me the new image, the image in orange or yellow or whatever color that is, goldenrod, I don't know, eggshell. The new coordinates for that image are defined in the upper left and lower right corners. So that's what we do. And that's what that returns. So this image right here is the original black square. This is a new image object that is representing this goldenrod square. This image is not changed. It just takes that image, returns that part of it. Okay? So that's cropping. A tuple with 4 arguments. Resizing is different. Resizing takes the whole image and makes it smaller or larger. Now, a lot of people don't think about how this works, right? If I have a pixel, an image that's just say 100 pixels by 100 pixels, and I want to resize that same image so that it looks the same down to 50 pixels by 50 pixels. Am I shrinking the size of the pixels? No. What am I doing? How do I compress it though? If the pixels aren't themselves shrinking, if it goes from 100 pixels to 50 pixels, where'd the pixels go? If I had 100 before and I have 50 now, where'd the pixels go? They're just gone, right? So I'm basically taking every other pixel in every row of that image and throwing it away. I'm doing the same thing vertically. Taking the number of pixels goes from 100 to 50. I'm taking every second row and just throwing it away ruthlessly. That's it. That's resizing, folks. You're taking more information and you're making it less information. So with that logic, if I take an image that's 50 pixels by 50 pixels, and I say, well, it'd be cool if that image was bigger, so I'm going to make it 100 pixels by 100 pixels. What did I just do? Where did they come from? Magic? Most of the time, it's a very basic algorithm. It basically says, "Hey, every pixel, now you're doing double duty or quadruple duty, in fact, because I'm taking 1 pixel and I'm saying, okay, now you're 2 pixels, and now you're also 2 pixels this way, which means every pixel is 4 pixels now." Did I add any real information to that image? No. That's why if I take a small image and I make it really, really big, it looks crap. Why? Because you can't do that. Except you can. Now, 20 years, 30 years ago, right? For the longest time, you could watch any old movie where there are like CIAs. Watch the original Mission Impossible when Tom Cruise looked exactly the way he does today, because for some reason he doesn't age. There's always this part of a movie, right, where somebody does something bad, and they get this terrible, like 100-yard away, really dark, blurry security cam photo of a person, and they're like, "That's the guy who did it," but we can't really see his face. What's the next line? Enhance the image, right? Like you're going to take this really crappy, low resolution, nothing image where you can't even make out their face. And you're like, enhance that. And all of a sudden, you can see the stubble on their face. Is that real given what I just told you? No. Here's how it can be. Now, first of all, there are what we call image resampling algorithms that do a little bit better than just saying, let's quadruple every pixel. The other way is a little bit more dangerous, because AI, if you say this is a face and we think it's a guy, so you AI, think about all of the other faces that we've trained you on. We've trained you on 800 million male faces. I want you to take a look at this blurry cam picture and tell me what you think this guy looks like based on the small bit of information you have and the million hours of training. Now, is that really enhancing the picture? No, that is guessing. It might be intelligent guessing, but let's just say if the AI, let's say the person in the picture, I'm going to reverse things. Let's say the person in the picture is a white dude. And my AI has been trained on 800 million faces of African American men. How good do you think it's going to be at correctly guessing what that white dude looks like? Absolute trash. Am I right?
Isn't the opposite how I got that really famous example of an AI thing that thought that like turn Obama into a white guy?
That's exactly the problem with AI, in fact. Why is it a problem? Because AI is trained on what's on the internet. It's the single largest source of information for training all AI. And what is most of the content online? Hello, it's me. But then all of a sudden AI thinks that this is what people look like. Sad. But that's the problem, is it is absolutely 100% garbage in, garbage out. It's one of the reasons why I'm a really big proponent on huge diversity in all software development. Why? Because our software is going to suck if we don't have that piece. We need more women. We need more people of color. We need more of everything. Why? Because the absolute quality of everything we're doing right now, which we're making some pretty big decisions using AI, it's a little scary, has to be good. And to be good, you have to capture all the full range of human possibility. So, back to resizing, off my soapbox, right? An image resize can be larger or smaller. In this case, you can see it's got the double parentheses, which says it takes one tuple as arguments. But instead of putting absolute numbers in there, I'm using floor division to convert the image width and the image height to a smaller number that is proportional. So if I use this, if I say image.width divided floor divided by 4, that will divide it by 4, throw away the remainder, and give me an integer. Because pixels have to be integers. I can't have half a pixel. Same with image height. So that allows me to scale the image proportionally. If I say 2 on the first one and 4 on the second one, it won't be proportional. If I just give it static numbers, which I can definitely do, and I don't get the proportions of the image correct, then the image is going to be squished or stretched or weird. So I can do that. I could say image width times 4, image height times 4, and it would scale it up. Now, if I want, when I'm resizing the image to make it larger, if I want it to be higher quality, I would give it a second attribute, which is a named attribute called resample. And resample says, use this specific formula for resampling the image and making it larger. It will result in higher quality. Limited higher quality, but still higher quality. So nearest bilinear is just an algorithm. It's a mathematical formula for resampling images that's better than just let's quadruple every pixel. So it's taking the bigger image and making it smaller by getting rid of data, or taking a smaller image and inserting data to make it larger. So really quick, let's take a look at this. So I can take the image and I can crop it here. And let's go ahead and say, yeah, let's just use those coordinates. I have no idea what they're going to give me, but let's do it anyway. So I'm going to pop open the image afterwards, image2.show. So I will show the original and the cropped version. So there is the crop. Okay, it's the same size as the original, you can see here. Same size as the original, same number of pixels that's in that area of the original, but just a subsection of that image, its own image object. In the same way here, I can resize that image. So I can divide it by 10. That makes it pretty small. So there's the original, and here's the small version. It looks like a pretty good quality smaller image, right? Like it did a good job as long as you keep it that size. But if I zoom in on this, you can see those pixels there, right? There you go. There's the pixels. So if I take that same strawberry, now you can see the difference, right? So let's enhance that. So that is resize. Now we've got a lot of others here. Let's see. Uncomment that piece. Let's see what else we got here.